exercise to do. Okay, so finally we'll turn to the situation that we were left with in the last screencast, which is different generating sets. You see, our problem with associating Cayley graphs or groups or word metrics to a group was the following: that if I take a group, okay, and then say S prime are generating sets, okay, then we had two constructions. First of all, the word metric and the Cayley graph, which had their respective advantages, but more seriously, for different generating sets we got different metric spaces. Okay, so we have already seen that the word metric and the Cayley graph are quasi-isometric. Okay. In fact, K could be taken as 1 in that case, since we have an isometry. But in fact here, I should emphasize finite generating sets. I assume the group is finitely generated and I've taken two finite generating sets. Otherwise this is very easily false. So G comma ds is quasi isometric to G with respect to S prime. Okay, so let me sketch the proof. I'll point out the main step in the proof. The main step, where do we use finiteness? Okay, so we look at the set of all generators S in S and look at their S prime norms. Okay, norm with respect to the other set. What do we know about the norm with respect to the other set? We don't know much actually. For example, it could be very long, but we know these are finitely many numbers. Okay, so if I take their maximum, this is still a finite number. This is a finite number, in fact an integer the way we have set up, but finite real matters. Okay, so what does this mean? So this means that S in S implies that norm of S prime is less than or equal to K. But recall that norm S with respect to S is equal to 1. So for generators, at least, when the norm is 1, the S norm is 1, the S prime norm is at most K. So you can guess from this that we are scaling up by K. So for G in G, norm S prime of not S but G is less than or equal to K times its norm with respect to S. This is what I'll prove and leave the rest as an exercise. So suppose norm G equals N, then what do we know? G is going to be S1 to the epsilon 1, Sn to the epsilon n, Si in S. So now we have our triangle inequality, or rather that property B or something of the norm. So norm G S prime, well, it's less than or equal to norm S1 S prime. Now I dropped epsilon I because of the symmetry property of the norm, plus Sn norm Sn of S prime. Now each of these is less than or equal to K, so this is less than or equal to K times N, which is K times norm G. Okay. So this concludes the proof of the lemma. Well, we can also do it in the other direction, okay, and find another constant and take the bigger of the two, as we usually do. You can find K prime so that reverse inequality is true, and using these you can pass from norms to distances and complete the proof. So this is the key idea. The point I wanted to emphasize is the finiteness is used simply by taking norm over a finite set, and that contains all the information. Okay.